some interesting features about transmission lines. Also, things like resonance, impedance. And really what we're going to talk about is the total antenna system. And that's just not the antenna, but it's the coax and anything else that's in that line. You may have a matching network, you may have various connectors and things of that nature. So the antenna system is really the important thing we're going to look at. And we talk about that because usually you're measuring SWR at the shaft end of the coax. So it's the coax and antenna and everything else. We're going to talk a little bit and demonstrate some standing wave ratio, SWR, right? And typically with an SWR meter, if you have that meter itself, not the antenna analyzer, but an SWR meter, it measures what? VSWR, voltage standing wave ratio. A lot of those newer models have also forward and reflected power and maybe a cross needle display that shows you the SWR right there. It's very convenient. Anyway, in the ideal world, we would like to achieve the lowest SWR possible, and it's always a ratio, so we're looking for a 1-to-1 ratio. And that means the antenna, the coax, transmitter are all 50 ohms. We can achieve that 1-to-1 ratio. And that's 50 ohm impedance, and we'll talk a little bit about that and show you how the meter measures that stuff. It's not always the case that we have 50 ohms, though, because you might be off the resonant frequency, the antenna may not be exactly balanced or whatever. So this is where we're trying to achieve 50 ohms, and that's where antenna tuners or a matching network come into play. And that's typically at your transceiver. We use that tuner to match the impedance in the antenna system, the cable and antenna, so we can get 50 ohms for our transceivers. In mismatched lines, you might have an SWR of 2-to-1 or 3-to-1. And what happens in that case? Well, a 3-to-1 SWR means that maybe 25% of your power is not getting to the antenna the way it should. In the case of a 40-meter dipole resonant at 7.15 megahertz in the 40-meter band, the SWR might be 3-to-1 over the entire band. In other words, the ends of the band might be 3-to-1 and the resonance might be 1-to-1. So that bandwidth is, basically something we have to deal with on the other bands. Take 80 meters, 75 meters. Typically an antenna can't be have that bandwidth over the entire band. Certainly not at 10 meters either. But if you can get it down to 2-to-1, that's maybe 10% of the power is not going to get to the antenna the way it should. But SWR really represents the amount of mismatch along that antenna system or in that antenna system, right? Well, basically the mismatch is what? Well, it's caused by impedance changes. And I just said before, we'd like 50 ohms, right? Your transceiver is 50 ohms, your transmission line is 50 ohms, and you want your antenna to be 50 ohms. Well, if something is not, and maybe it's the antenna, that gives us a standing wave ratio. And what is that? All right, we talked about standing waves. The standing waves come from reflected power, and it's reflected basically at the antenna coming back, or wherever that mismatch is, where it's not 50 ohms. In this case, that reflection at where the impedance is different and where it's not 50 ohms is reflected back from the antenna towards the transmitter. And some of that power that gets reflected back at the transmitter also gets re-reflected back down the line towards the antenna. Now here's what happens. You have a certain amount of power coming from the transmitter going down to the antenna. Part of that power will go to the antenna itself. If it's not 50 ohms, not a perfect match. Part of the power goes to the antenna. Part of it gets reflected back down the line, comes back to the transmitter, and gets re-reflected back. And this sets up the standing wave in your transmission line. The standing wave can be much higher voltage and much higher currents wherever that standing wave has those peaks of voltage and current. And that is something to consider because transmission lines have a spec as to how much voltage they can withstand. Also, a short or an open in your line will have that impedance change. An open, very high impedance, a short, very low impedance. The transmitter doesn't see the 50 ohms anymore. Wherever that impedance change is, will reflect the power back again. So antenna systems with high SWR have what I've been talking about, and that's the reflected power. The reflected power, when your original power goes down the line, some of it is lost in the line because we know that transmission lines have loss, and certainly at higher frequencies they have more significant loss. So the power going down the line, first of all, goes down and you have a certain amount of loss. And how does it get lost? The resistance of the line gets lost as heat in the line. Not that your line gets hot, but the transmission line does dissipate some energy. When you have the standing wave and you have power being reflected back and forth, that has to travel the length of the line again, and you lose more energy. So high SWR tells you that you're going to be losing power in your transmission line. Also, I think everybody knows that high SWR can cause problems with your transceiver, and that is the finals in the transceiver, or if you have a pi network, or if you have an antenna tuner, there's a lot of reflective power can also cause problems with that. Matter of fact, I did that once. On 160 meters, I had my 75 meter antenna and said, I want to try it on 160 because this particular CW station don't want to work. Sure enough, I tried to tune it the best I could. What happened? I had so much current in the coil on the antenna tuner that it unsoldered one of the taps I was using. And I opened it up after that, and I had to repair that. That was quite something. Anyway, this is one reason why we'd like to have low loss line, and or you might have not only low loss coax or hard line, but you can also use a ladder line, window line, things of that nature, which are really low loss. So if you've ever looked at a table of coax, I don't know, Johnny, can you bring that one up? I'm going to put it up on the screen, but I'm just going to read a couple of things. This is a coax table showing you the loss at particular frequencies. This may be hard to read, but I'm going to make this available in the stuff we publish. But I just wanted to say that if you take something like RG58, which is an old coax we don't use very much anymore, but at 2 meters you have 6 dB, and it says 6.1 dB loss per 100 feet. Well, what is 6 dB loss? We know. Excuse me?
Double it up.
Well, yeah, 3 dB is half your power lost in the cable. If you're transmitting 50 watts down the cable on 2 meters, only 25 watts is getting to the antenna. If you have 6 dB loss, it's half of that again, only 12.5 watts is getting to the antenna. So we don't want to use RG58 on 2 meters. Don't want to do that. Fortunately, RG858 is not around much anymore. People don't really use it for much of anything. But RG8X is another important coax, and we use a lot of that today. But also on 2 meters, you see it's 4.5 dB. Well, we know 3 dB is half power, and another 1.5 dB is even more. So that RG8X is not really great for 2 meters. Certainly, you don't want to use it on 440 either. But you take something like RG213, which has a loss of 2.8 dB. That's getting a little bit better. Or LMR400, 1.5 dB on 2 meters per 100 feet. That's a good cable to use on 2 meters. All right, we're going to go away from this table because you could read it all night and be entertained by all these numbers. But let's talk about the antenna analyzer and the dipole. Well, we know a dipole in free space is about 73 ohms. But as you lower it down to Earth, it changes the impedance in that dipole. And if we wanted 50 ohms at our dipole, well, you could move it closer to the Earth to get it to a region where it's approximately 50 ohms, and that's 1/10 of a wavelength. off the ground. Well, that's not very useful unless you're using it as an NDIS antenna, right? You want to go straight up and do local work. But if you want to raise that antenna to a half wavelength or 1 wavelength, it's more like 70 ohms. Well, now we've got a 50 ohm coax, we've got a 50 ohm transceiver. How do we get this 70 ohms? Well, that's where you'll be using an antenna tuner at your shack end of the antenna system. And so that brings us to the antenna analyzer to help us understand what is happening at our antenna and what this antenna system is doing. So for this type of antenna analyzer, which is the MFJ, and some of the others we'll look at here in a few minutes, this one, it basically puts out a few milliwatts of RF power. Typically 1 volt open circuit and about a half volt at 50 ohms, because this is 50 ohm impedance, and you put a 50 ohm load on it, and you pay about a half a volt. It also has a frequency counter in it, so it's got an RF generator, it's got a frequency counter in it that reads out on the dial here, on the readout. It's got a 50 ohm diode bridge in it that does the measurements. That will give you, the SWR, the impedance, reactance, resistance, things like that. It's got a microcontroller in it to do all this analysis with a A to D converter. It's a 12-bit A to D converter. And with that microcontroller, it calculates the impedance, cable loss, SWR, and then you've got some meters too to help you read the SWR and the impedance. So that's basically what it is. Now there's a lot of uses, but we're only going to go over a couple of uses tonight. And we're going to start with the SWR, because that's one of the most important things we can understand about our antennas. So to do that, I have an antenna. This is a 2-meter antenna, or something close to a 2-meter antenna. And if we put it on our SWR, if we put it on our antenna analyzer and look at the SWR, and we're going to do that now, we can get this all to work the way we have it planned. I'm going to put it over here. So,
okay.
Yeah, see if you can get it.
Oh, I'll get it.
Well, the first thing we're going to do is we're going to measure the SWR at 147 megahertz. And hopefully we keep it away from enough things so we don't interfere with this. And if you can see the readings on the screen, we are at 144 megahertz. Let's bring it up to closer to 147, sort of where the SPARC repeater is. And if I wanted to use it on the SPARC repeater, I might hold it in a vertical orientation. But we're seeing that the SWR is like close to 3. All right, well that's certainly not a real useful antenna, because any length of coax with SWR 3 to 1 is not going to be very good. We're going to have standing waves that are going to lose some of our power. So let's do the next thing, and that is find the resonant point of this dipole. Where would it be resonant? Well,
above or below.
Above or below, right. So we're going to go one way or the other. Well, let's go up. Okay, up. Oh, SWR is getting higher. Well, that's not the way to go.
How long is that antenna?
Long enough? Now, let's go down in frequency. So we're going down in frequency now, and hopefully the SWR will decrease 1.7 to 1. 1 to 1. Well, just about 1 to 1. Let's see. That's about the best we're going to get. It's a resistance of 45 ohms and the reactance of, well, it says 1 ohm now. 49 to 1. So that's basically 1 to 1. But the frequency is 137 megahertz. Well, that's not very useful. Not very useful for what we want to do. Well, if I was at the 3 to 1 SWR up here at 147, and I put, let's see, a 100 feet of RG8X on it, I would have some significant loss. But this 100 feet of RG8X, we can find out what the loss is if we don't know how long it is, because we know there's a certain amount of loss in the chart per 100 feet. We can find that out using the antenna analyzer. And the way this is done, it's done by taking the coax and leaving it opened or shorted at the far end, connecting it to the antenna analyzer, and in this case,
Does that need to be stretched out, or can you just have it in a wad?
it can be in a wad. In this case, you want to go to the next mode, and the next mode will be the antenna loss, or coax loss. So in this mode, at this frequency, 147 megahertz, the loss in this 100 feet, well, I think it's 100 feet, or maybe it's a little bit less, is 3.5 dB. Well, we said 3 dB is half your power, right? So this RG8X cable on 2 meters, half my transmit power is going to be lost just in the cable eating it. You could have it either way. You can do it either way with this, the instrument. And the reason is because you want all the power reflected. This meter will then measure how much power comes back as to what it sent down, and it calculates the loss. And we know that a short or open is an impedance change from the 50 ohms you would expect. So I have no 50 ohm load on it. In this case, it's open, or you could short it. Okay?
It
So-
doesn't matter, and you're gonna have to change the setting.
Well, I've changed the, the one thing I could change is the frequency. Now, if I go down to, let's say, 10 meters, or, well, I'm not even going to take time to do it, because if I go down to HF band frequencies, the loss drops off a lot, and that's why we use RG8X at HF frequencies. So, in doing that, we know that if I use that 2 meter antenna I just demonstrated, which is, you know, it's the resonant frequency is really low, and you've got SWR pretty high at the, let's say, 147 megahertz, and you use this cable, you're going to end up with a fair amount of loss in the whole antenna system. Well, if we take a piece of better cable, RG213, which is this one. Now, this piece of cable came from one of our members who is currently SK. It was taken down from his setup. And he had it underground, I guess, in a plastic pipe. And this is not really meant to withstand water, but there was water in that pipe. And this part that was the far end and in the pipe is pretty brittle now. As a matter of fact, this is what it looks like. Here, why don't you pass this around? Send it around to everybody. Take one. Pass this one in this direction. You see what happened to that braid with water in it. That braid is now black. It's totally oxidized and stuff. But if we take this and connect it to our antenna analyzer, we'll find the loss of this cable. Now, this cable has dried out, so it's not as lossy as it might be. Let me get this cable out of here. Well,
Want a knife?
yeah. See,
Here.
Cut that off. Oh, here comes Mike too. He's got his out.
Mike's is sharper.
Yeah, cut that out. Yeah, excellent. All right. So, we can measure the loss in this cable. I don't know, it's like maybe 40 feet or something. And again, we are, oops. All right. So on 2 meters right now, we're seeing that this cable, even though it's a good cable, RG213 should have lower loss than this. This is still 2.4 dB, close to 3 dB, half power. We don't want to do that. Don't want to use this cable either. So that's the, that's one way to do it. So we've measured SWR, we've measured cable loss. 2 important things you can use this meter for. All right? Another thing you want to use the analyzer for is to tune your antenna to a low SWR, right? So let's get the antenna back here. There are many other functions. If you look at the meter itself, I'm going to go through some of these other functions real quick. I'm not going to demonstrate them. But can you get a tighter shot?
Mm-hmm.
So we're looking at coax loss right now, but the next function is measuring a capacitor, picofarads, and you could do that. Measuring an inductor in microhenries, and these are just components you can measure. Frequency counter, we can put a little antenna on this or feed a frequency in and measure it. And we're going back to our original setting of impedance, which gives us SWR, and here we are at 147 megahertz. The SWR is real high, 3 to 1. So we can use this to tune our antennas. Well, we know that the antenna is resonant at a lower frequency. That means it's what, too long or too short? Too long. So let's make it shorter. So we'll make it shorter. What happens to the SWR? Went down to 1.1 to 1. Very nice. But
It just slides back in on that antenna?
no, I just folded the end over. One thing you might ask yourself is, hey, what did you just do? I folded one end over, not the other end. One end's shorter than the other. Well, that's not really a good antenna, and it kind of tells you in this, and we're getting some interference, it kind of tells you that the resistance is kind of low, and it's not really 50 ohms. And you can get closer by making this a little more symmetrical, and that's what we want to do. So about yay much this end and about yay much this end. This is my scientific calculated process of tuning an antenna, and we all do this on our HF antennas. Cut, fold a little back and tie it off. All right, so now what do we got? Well, very close at 49 ohms, and the reactance is 1, 2. This is nice. This is how you'd like to use this antenna. Okay? 1-to-1 match. SWR is in the right-hand corner. It says 1.0, right? That's 1.0 to 1.
The R is the resistance,
That's, yeah, 50 ohms. I couldn't ask for better than that, huh? By my scientific method of IX, the SWR will be really high. Yeah, watch it now, see? If I touch it,
oh, you're messing it up.
yeah, see? X goes up to 16, your reactance goes up, and yeah.
You're a high load guy.
Don't do that. No, don't do that. All right. Yeah, you probably will because there's metal up here, and I'm near it, so like, yeah. So that's so we've tuned our antennas, right? Okay, good. And we found the resonant point before, and we now have the resonant point where we want it. SWR is low. Okay, I have one more demonstration that I think is very important, and this is finding, when you go make a coax cable up, and you put your connectors on it, and you go to use it, and it's shorted. Then what do? Yeah, start over. You buy a cable from a manufacturer, and you get it shipped to you, and it's shorted. What do you do? Well, let's see. I think this is the cable I used before. All right, so this is what, about 50 feet of RG8X. And I've got my short right here.
How do you know that that's where your short is? You make it.
Well, I'm gonna tell you this. Your short is at one end or the other because you believe the connector is bad. Somebody did a bad job soldering it. You didn't do a bad job.
Not a very common occurrence, right?
Yeah, right. All right, this little barrel connector I'm putting in has a screw and a washer in the end that is soldered over to the edge. So it's a short, that's short. And I'll put that in there. Come on. Okay, that's good. And then I'll take the other end. So now the question is, how is the meter going to tell us which end is shorted?
What end you get them changed?
There is a function on this meter that is basically a distance to an impedance change, and you can use that function, and other people know it as a time domain reflectometer, TDR, and that could show you the distance to the impedance change or the impedance bump. In this case, we're going to do something a little different. 50 feet is what? About quarter wavelength, I think, is somewhere around 9 megahertz or something. So I'm going to put it in here, and I'm going to say that I'm using it on the same scale we had before, measuring the SWR, measuring and changing the frequency. And I'm going to change the frequency band down to where we want to be, roughly. And because we have a short, in this case at the far end of this 50 feet, we're going to get a reflection back, but it's going to be at the frequency that this is a quarter wavelength. And if I sweep this a little bit, we might be able to see that. Well, we should see it. I don't know if this is my same cable I used earlier, but you will find a place where it will give you a change in SWR. Don't fail me. Come on now. Let me go to another range. Let's see. Let's try it here. No, it's too low a frequency. Let's go up in frequency. This range and this range, go up here. Try it this way. Well, not there either. You can see at this frequency the ohms go all the way down to 0, right? And 13 megahertz. Is my other cable here? Do I have my other cable? No, not that one. Yeah, I didn't bring the other cable I used this on. I'm not sure the length on this one, so I'm guessing at the frequency.
Let me get back in there.
But what we saw in the resistance goes way down at this particular frequency, and you can do a rough calculation to get the quarter wavelength and convert it to, measure the length of the line and convert it to feet, convert the feet to a quarter wavelength, and that if your frequency dips at that point, if it basically tells you that the short is at the far end, because if it's right at this connector at this end, you're not going to get that dip at all. I mean, no matter where you scan the frequency, you won't get that dip in impedance. And do I have something to show you that? No, I guess not. So that's pretty much how you can find the which end is shorted before you cut it off and start again. And it does work, because I did it really nice on another piece of cable. I guess I left that one home. But you can do that. Now you can use the other function That's the distance to the short function, and we may cover that in another presentation. We might do that in the summer or something else. Bob and I have worked on a couple other aspects of using the meter, and I think there's enough material there, like using those advanced functions, and we could demonstrate some of that. There's a couple other things I want to demonstrate, though, and that is, what about these antennas? What about these antennas? And what you can't see here, Walt, is these are little antennas from your HT. Well, they should tell us something, right? Or we should be able to learn something about this. All right, well, here's a nice Nagoya antenna, which you might be using on your HT, pretty popular. And with the right adapter, this little Nagoya antenna, what I'm going to do is I'm going to hold it up for this one because I'll bring it over and put it there to show them.
Oh no, you just stay right there.
All right, put the adapter on here and we'll get this. So we would expect this to be resonant where? 2 meters, right? All right, so on let's see, we'll get...
Maybe 440 too.
Maybe. All right, let's get back to our 2 meter range, and I'm going to see if we can get this. All right, so let's see, we're at 70, and SWR is real high. We're going up to 90, 110, and I got to get on another range. Sorry about that. Now we're coming down to 2 meters. Here we go, 2 meters, and we're at SPARC frequency on 2 meters, and it's 3.4 to 1 SWR. Not so good, huh? Okay. Where is it resonant? Well, let's bring the frequency down. It's resonant down here at 141. Oh, that's not such a great antenna.
This will on this box.
Yeah.
This resistor value is 8 ohms. The X, the inductance value is 20, and the Z is 21. So it basically shows you what's what. If we change this thing, oh yeah, see how the numbers change.
Yeah.
That was capacitive. Now it's inductive. And we should be able to tune this thing down to. It's pretty sensitive. But that's what.
Right. What we're going to do is find the short in the cable. The short we're assuming is at either end of the cable in the connector because it's probably a bad solder job or something. But if you have a cable that's got a short in it, rather than just arbitrarily cutting one end off, you can find which end or which connector has the short by using the antenna analyzer. So for demonstration purposes, Josh has the end that's shorted here, and I've connected the other end to my antenna analyzer. For the antenna analyzer, what we're attempting to do is, and we can measure the length of the cable, we want to find the half wavelength frequency, the frequency which this would be a half wavelength. And I'm going to tune a little bit to see if I can get past that, to get to that frequency. And as I'm tuning, I'm lowering the frequency here. I'm at 15, I'm at 14, and what we're seeing is the resistance is going down. And we'll notice here the resistance is 1, almost 0, and the reactance is very low as well. So at this point, that's the resonant frequency. Now, what this tells me, because the resistance and the reactance dips, it tells me that the short is at the far end of this cable, because the cable is basically a half wavelength at this frequency. as I turn the frequency, you can see the resistance goes up and the reactance goes up as well. Now, to confirm that it's that end of the cable, if I put the short here, and Josh, if you'll take that off, if we reverse the cable, because now we suspect that far end is the short, I will put the short on here. This assume this is the cable with the short end. Just put the other. This barrel connector on the end has a little short in it. It's a screw and it's soldered over to the outside edge. That's our short we're using. And what you'll see here to confirm that it was that far end is as I tune the frequency, it remains 0 because the short's right here at the meter. So the whole key to this is to see which end has the short. If it's the far end, you'll be able to find the resonant frequency based on half wavelength of the length of this cable, and you can figure that out and measure the cable, and you know what the frequency you should be looking for, as I did to begin with. So that's how you do it. Antenna, dipole antenna. It's a bazooka antenna, a double bazooka actually, and we're trying to verify that it's resonant in the 10-meter band.
28. What are you going for frequency-wise?
And well, I'm going to 28 something, and I'll get there.
28,400 is.
Yeah. So if I'm at 28, going up to 27, I'll go to my other range.
Charge the battery on this one.
Yeah, okay. Coming down to 30. So what we have at 30, the top of the band, is still SWR over 3 to 1, but as we come down to 29, it's around 2.4 to 1, but still high impedance. And then when we come down to 28, 300, and we're standing a little close to it, if we back up a little bit, we get 28, 500 is about the lowest point. Yeah, 28.5. So the resistance is close to 50 and very low reactance. So we could tune this antenna a little bit more by shortening the ends if we want to move it up the band. All right, that's good for that.
There you go, you found the resonant.
Yep. And then we can do.
It's pretty nifty. Don't even have to really look. You just put it on and it maps it
Well,
out.
it actually has. All right.
That 6 meter J pole that you lent me,
it
it'll
shows
do 10 meters with a tuner.
it shows it bouncing around a little bit, but that's your. Yeah.
I only have
well,
it on my fence right now, and I can barely hit Seminole.
All right.
This antenna is not perfect, I know that. You could use a little tuning. So we're going to go up to 2 meters. We're trying out a J-pole antenna, and we're seeing what the SWR on this one is. So we want to go up to 144 megahertz, and we're not doing it on that scale. We should be able to. Okay, here we go. 120, 130, 140. So we have a resonance at 143 megahertz, 50 ohms, very low reactance. And so this is cut a little low for 2 meters. We were hoping to get more like 147 megahertz or 146.
Yeah.
But up there, the SWR probably goes up to, well, goes up to not too bad. It's 1.5 to 1.
It's not too bad.
So it's usable.
Very much so.
All right, let's see what Josh's antenna looks like. And we are going to raise the frequency up to 147. It looks like it's dead on. 147 is the about resonant point. So this is good.
Yeah.
You cut it well. So your J-pole, Josh, is working pretty well there. And matter of fact, if you go down to the low end of the band, well, it starts to
Yeah.
creep up, but it's still 1.5 to 1 or so. It's in that range. And if you go up to the top of the band, it also goes up to about. So you got to cut pretty much in the center of the band. So we're good on that.
Yeah, right.
SWR very low at 1.1, 146.7. So that's good. And Bob, you want to try that?
Yeah.
So many different kinds.
Here's the
Oh,
scan.
yeah.
Scan.
Good. Yeah, it does.
Oh wow, just scans it right there, and it,
Yep.
and then it centers on the lowest point.
Well, no, I can move that. You said it was 147, so that's where I put it. But I can, I can.
It's not a bad waveform.
If I can move
No,
the range out and redo it again, it'll widen it.
Woo!
See,
That's super wide. Okay.
I widened it out, but that just shows you how good you are. It's
Cool.
doing a job.